In this second half of the lecture on gas laws, we'll start with Charles's law, which defines the relationship of volume and temperature. It is a direct relationship, just like we saw with pressure and temperature. So if temperature increases, volume increases. If temperature decreases, then volume will decrease. So our formula is very similar. V1 over T1 equals V2 over T2. Again, our temperature must be in Kelvin. Our units for volume do not matter. You may have a volume in liters or milliliters. Occasionally you might see liters in cubic centimeters, in volume in cubic centimeters. Cubic centimeters is the same thing as a cc, which is equal also to milliliters. So you can have different units for volume, but they don't really matter in our Charles's law equations. So I have a problem now. A sample of carbon dioxide occupies 0.300 liters at 10 degrees Celsius and 750 torr. What volume will the gas have at 30 degrees Celsius and 750 torr? They throw our pressure in there, but we see that it's the same before and after, so we don't have to worry about including the pressure in our equation at all. What I do see here is that I have a volume, I have a temperature, and then I'm asked what volume will I have at a different temperature. So this clues me in that this is a Charles's law problem. So I'm going to write out my variables just like I did when I worked the first problem. So my first volume is 0.300 liters. My initial temperature there is 10 degrees Celsius. I'm looking for the volume, and I'm given a second temperature of 30 degrees Celsius. Now again, my first step in this is to convert those temperatures to Kelvin. Remember, they have to be in Kelvin or our equation will not work. So now that that's done, I'll just set up my formula and plug in my numbers. I'm solving for V2, so I'll just leave that in there. You know, that's what I'm looking for. Again, I cross multiply. I divide both sides by 283K to get the volume by itself. Notice that these will cancel out here. My units for Kelvin will cancel out there, and I'm left with liters, which is an acceptable unit for volume, so I know that I've got my problem set up correctly. So now I multiply 0.300 times 303 equals, I divide that by 283, and for my answer I get 0.3212, and my unit there is liters. Now I look at significant digits. In this number here, all three of these are significant because these zeros are after the decimal point. This 0 is not significant, but these three are. So I need three significant digits in my answer. So I'll have 0.321 liters. And then remember, the last step is to ask yourself, does this make sense? And when I look at this, I expect that if my temperature goes up, my volume goes up, and yes, my volume did go up. It went up from 0.300 to 0.321. So now we'll look at Boyle's law, and Boyle's law is a little different than what we've seen with the other two. In Boyle's law, we have an indirect relationship, meaning that the variables are going to do opposite things. So when we look at pressure and volume, if pressure goes up, volume will go down. If pressure goes down, volume will go up. So we have a different type of equation here. Instead of dividing, we're going to multiply, P1V1 equals P2V2. So I have a problem here. The volume of a gas is 20.4 liters when our pressure is 925 kilopascals. At constant temperature, we get a change in pressure, causes the volume to change. Our new volume is 30.6 liters. What is the new pressure? So I see that I'm told that I have constant temperature, but I've got a change in volume. I'm asked what is the new pressure. So that's going to tell me I have Boyle's law. So I'm going to write down my variables. My first volume is 20.4 liters. The pressure is 925 kilopascals. They're asking me what my new pressure is. My second volume is 30.6 liters. With a Boyle's law problem, it does not matter what the units are. As long as your units of volume are the same before and after, or if we're dealing with pressure, your units of pressure are the same before and after, then it does not matter what the units are. So my equation is P1V1 equals P2V2. So I'm going to plug in my numbers here. I'm looking for P2. And now I'm going to divide both sides by 30.6 liters. My units of liter will cancel out. I'm left with units of kilopascals, which is a pressure unit, so I've got my problem set up correctly. So I'll say 925 times 20.4 equals divided by 30.6, and I get 616.67, and that's kilopascals. So I have to look at significant digits. I have 3 significant digits in all of my numbers, my values here. So I need 3 significant digits, which will be 617 kilopascals. Then I have to ask myself, does my answer make sense? Well, in Boyle's law, if volume goes up, then pressure goes down. My starting pressure was 925. My ending pressure is 617. So yes, my answer does make sense. Now we'll take a look at Avogadro's law. Remember, Avogadro is what gave us our number of atoms or molecules in a mole. And so when we look at his gas law, it's dealing with moles, and it relates moles of a gas and volume. And we see here another direct relationship where we have V1 over N1 equals V2 over N2. The N there, that N variable, is used to represent the number of moles of the gas we have. So here is our problem that we're going to work. And so we see we have 8.80 moles of helium. We have a pressure of 0.992, a temperature of 25 degrees Celsius, and we want to know what is the volume of the balloon under these conditions. Okay, I realized after I read that problem out loud that I got my slides out of order on my little whiteboard here, and that was an ideal gas law problem, which we'll get to in a minute. So now I have an actual Avogadro's law problem with moles and volume. So I have 5 liters of a gas. It's known to contain 0.965 moles. If the amount of the gas is increased to 1.8 moles, what new volume will result at unchanged temperature and pressure? So they tell me my temperature and pressure aren't changing, so I know that I don't have to worry about those variables. I have liters, I have moles, so I know that I'm going to have an Avogadro law problem. So I'm going to write down my known values for my variables. So my initial volume is 5.00 liters, and I have 0.965 moles of that. And we want to know the new volume. That's what they're asking for. And I have 1.80 moles of gas now. So V1 over N1 is equal to V2 over N2. So my initial volume, 5.0 liters, initial moles, 0.965. I'm looking for my V2, so I'll leave that as a variable. And I have 1.8 mole as my N2. I'm going to cross multiply. So I have 5.00 liters times 1.80 moles equals 0.965 moles times V2. I'll divide both sides by 0.965 moles. My units of moles cancel. I'm left with liters, which is what I'm solving for with volume. So I'll multiply 5.00 times 1.80 equals, divided by 0.965, and I get a volume of 9.326, and that unit is liters. So I look and see how many sig figs do I need. Well, I've got 3, 3, and 3. So I'll round 9.33 liters. Last step, does my answer make sense? Yes, it makes sense. My moles almost doubled, so I would expect my volume to almost double, and it did. It went from 5 to 9.33. Now sometimes you might be given grams of a gas and volume. Well, if you're given grams and volume and you think, oh, I don't know what to do because I don't have any gas laws that involve grams, but we can easily convert grams of a gas to moles of a gas using molar mass. Then you can use Avogadro's law, or you may have to do that also for the ideal gas law, which combines all of the 4 gas variables into one equation. So we have PV equals nRT. So our pressure will be in atmospheres, volume in liters, N, our number of moles, of course, is going to be in moles, and then our temperature in Kelvin. So the ideal gas law is very specific about what units you must use, and that's because of that R variable, which is referred to as the ideal gas constant. And it is equal to 0.0821 liter time atmosphere divided by mole time Kelvin. So our other units have to be consistent with those so that we can cross those units out in our ideal gas constant so we can solve for exactly what it is that we're looking for. So now we'll get to the problem that I read a while ago about our weather balloon. And so what I'm going to do is I'll just write down all of my variables here and my ideal gas constant, which I know is 0.821 liter time atmosphere divided by mole time Kelvin. And I'll write down those others. So now I have all of my variables written here and my question mark on my volume because that's what I'm trying to solve for. I've plugged in all of my values into my PV equals nRT equation, and I have this all set up. I've divided both sides by 0.992 atmospheres so that I can get volume by itself. Now, the reason why it's important that we have these units as we do is so that we can cancel them. So moles cancel, kelvins cancel, atmospheres cancel. I'm left with liters, which I know is the unit for volume. I know that that's what I'm solving for. So when I plug all of this in, I'll say 8.80 times 0.0821 times 298 equals divided by 0.992, and that gives me 217 liters. And I see that I need 3 significant digits. I'm going to look at here this number and this number. We do not consider our R value here when we look at sig figs or our temperature, so we'll use 3 sig figs. So my answer is 217 liters. In this one, we can't really ask if it makes sense. We only do that with the others.